Hi everyone, my name is Pinchu Lai. This is a study about epidemiology of spotted wilt disease of peanut, SWP, and impacts on peanut yield. SWP is caused by thrips-transmitted tomato spotted wilt orthotospovirus, TSWV, which could lead to severe stunting of plants and yield losses. We have seen an increase in disease incidence in modern resistant cultivars in recent years. However, data-driven economic impacts were never documented. Yield loss estimates were rough inferences based on limited studies. Understanding how SWP spread in time and space will help us better assess economic impacts of the disease. The objectives of this study are to describe SWP progressions in time and space and to estimate yield reduction by SWP. Peanut cultivars, Georgia Green and Georgia 06G were planted in 2018 and 19 in Tifton, Georgia. We rely on natural occurring TSWV and vector pressures for virus source. We use sticky cards to monitor thrips populations. Every TSWV symptomatic plant was flagged using colors to distinguish sampling days. The amount of symptomatic plants and their positions in the field were recorded over time. At the end of the season, disease severity was rated before harvest, and peanut yield was compared between TSWV infected and non-infected plants. Cumulated disease incidence over time was used for temporal disease progression model fittings. Spatial and spatiotemporal disease distributions were analyzed using SEDI. The effects of infection time and cultivar on yield were analyzed by ANOVA. Relationship between disease severity and yield were analyzed by regression analysis. Here's what we found. Thrips populations, as shown in Figure 5, were high before 48 days after planting and drastically decreased afterward. Temporal disease progressions were presented in Figure 6. The overall SWP incidence was higher in 2019 than 2018. Disease progressed faster during 60 to 90 days after planting, indicated by the steeper slopes. This might be resulted from high thrips populations before 48 days after planting. Symptomatic plants are clustered, but the clusters were randomly dispersed in the field. This might be associated with landing patterns of immigrating virulliferous thrips, which appear soon after plant emergence. Significant spatial-temporal disease distributions were found as shown in Figure 7. Distributions of disease clusters were similar among sampling days. Along with increasing disease incidence over time, certain degree of in-field spread of the disease was suggested. Looking at the yield differences between cultivars, Georgia Green had higher yield than Georgia 06G. However, Georgia Green also had higher degree of yield reduction by SWP than Georgia 06G. Disease severity ratings were higher when symptoms were found before 62 days after planting than afterward. We found a negative correlation between disease severity and yield. When disease severity increased by 1 rating score, peanut yield reduced by 10% based on a regression model. Marketable kernel yield was significantly reduced when TSWV infection and symptoms appeared before 76 days after planting, as shown in Figure 8. Therefore, infections occurred before 76 days after planting, attributed to most of the yield reduction by SWP. Degree of yield reductions of individual plants range from 0 to 97%. The earlier the infection occurred, the worse yield losses we got. On average, SWP reduced 45% of peanut yield. In conclusion, our study provides fundamental knowledge of disease spread and economic impacts of SWP in modern peanut cultivars. Future studies should focus on assessment of disease severity and yield losses to SWP in large plot settings, which can be directly applied to yield loss estimation in peanut production. Thank you for your attention.